Welcome back. So in the previous video we have already built the constructors, the default parameterized as well as the copy constructor, and we have also built this function that adds a fully connected layer called addFCLayer, and I also fixed a few typos here. I basically made some spelling mistakes here, like I used uppercase L for layers activation like this, and a lot of other small mistakes. So I fixed all of that, and in this video let's just try to build the activation functions. I will be using ReLU a lot. ReLU for classification problems we will use ReLU throughout the hidden layers, and for the output layer we'll use softmax function. So we'll use those two activation functions, right? But there are a lot of activation functions that you can use, like nanH and sigmoid and stuff, but we're just testing out. We're just building this library for for getting an idea how things look in C++, so we won't be building all the possible activation functions. So there's that, and let's just get started. And one more thing, I just thought I should also build a function that prints all the layer dimensions, like the dimensions of weights, activations and stuff, so you can get the the idea about what's going on under the hood. But I will save that for later when we try to test this layer, test this network on some test case, right, on some data, because it will be much more useful then. So let's just build activation functions. So the first activation function is ReLU, and let me just use this return type because we have already used auto. Let's just experiment with other things. So I know what it will return. It will return a matrix of doubles. So matrix of double, and let's just return reference because these objects are really large. We cannot go on creating copies, so it's a good practice to create references or use pointers to objects that are very large. So you don't want to create a copy of that entire variable, so you can just point to that, or you can just move around that object itself rather than copying it over and over. It will just use up a lot of space in the memory, and it will also take a matrix of doubles. That's straightforward. Let's just make it a reference, and this is our function prototype. Okay, so let's just go to the C++ file here and let's implement this. So the return type, the usual syntax, the usual syntax here, return type, name of the class, reference, and ReLU, its parameters, and let's assign it a name, layers. Okay, now layer dot for each. I'm going to be using a lambda function. So what lambda is, it is kind of a function that has no name and stuff. So well, for each is an algorithmic algorithms. Let me just put it in this way. The Armadillo library supports a lot of algorithms, and it has a syntax just like the STL standard containers. So for each is a function that takes in a function or a pointer to a function or a lambda and applies that particular function to each and every variable, each and every member stored in that. So layer is a matrix, and it will apply this particular operation that we are going to pass in for each, and it will apply to all its members. So if there are 200 elements in a matrix, let's say a matrix it contains just 200 elements, it will apply that operation to each and every single one of these elements separately. So the syntax for lambda, if you don't know, you can search it on the internet. It's very famous these days. So it's just this square brackets. It's mostly the parameters. You can leave it empty because we don't want any, and then the parameter that we need is lm type. Now what this lm type returns is, it returns the element type of Armadillo. It is a particular element type of Armadillo, so you can perform operations on that. If you don't get it, it's fine. You can just read the documentations. It's not very complicated, but it's not something that a beginner would get. So what element type is, let's say it's a primitive, or it's a data type on which the entire armadillo library works, right? So it is a particular kind of, it is a particular type of data, right? So it basically means that it's a type of data. It can be a double, it can be anything that we can perform operations on. That's just what it means. Okay, so here we have left this empty because we don't want a reference or a copy of any variable that is outside this function. This is what basically it means. And here we'll pass in the things that we actually need. So for each element it will just track this element type, whatever element that might be, whether it's some matrix of double, integers, or whatever that is. You can just perform this operation there. And we will, of course, we're using reference because we want to change that. And then there comes the body, which is curly brace, and then you will you can just define what you want to do here. So let's just say we want to set x is equal to 1 if x is greater than 0, otherwise we will set it to 0. But we won't set it to 0 because it sometimes oh sorry, I just got carried away. We're actually what I just said was we use that in the gradient calculation. So here what we'll do is, let's just say we will set x is equal to whatever is greater between x and the epsilon times x. Now if you forget what epsilon is, here we have already defined epsilon. See, whenever a value might go to 0 and that value is using for division, it creates error. So to save that, we just use epsilon. So in a lot of implementations you'll find this is kind of a leaky relu implementation if you're not familiar with it, but a lot of implementation just set it equal to max of 0xs and 0. So basically set everything to 0 if less than that. So yeah, but I'm setting epsilon in times x because I don't want a lot of variables to be 0, lot of weights to be 0, because that creates a lot of problem and a lot of numerical instability, and you'll realize that once you experiment with all of these things. So there's that. And let me just put in the curly braces, one curly braces for the statement and one curly braces for the function call, and let's just return the layer. So it seems complex, really complex right now, but once you understand what element type is, it is just accessing each and every element. So each and every element will be replaced here for x. X will store each and every element of the array every time this loop runs. It's a kind of a loop, like for each means for each of the elements. For each of the elements, track the variable and store it as x, and then set perform this particular operation on that element. So it will perform these kind of operation on each and every element. Now let's just, this was activation function, right? So we also need to deactivate or basically calculate the gradient of the activation function. So let me just do that here, and then we will edit that in the header file. So again, let's just use auto. Well, of course you should stick to one type of implementation, right? If you're using auto, then you use auto throughout, because it just gives you kind of uniformity in your code. But I'm just trying to experiment with this, all the features, so that I'm trying to use as many features as possible, so that you also learn about that, about the things that C++ has got to offer. Okay, so let's just write this network, and then I'll name the deactivation function as ReluGrad, because it is a gradient of relu function. Again, it will take matrix sorry, double, and again I'll name it a layer because it's again a layer. And let me just again perform this operation for each. I think we don't need anything from outside, but what we need is lm type. Okay, that's a typo. And then let's name it x again for uniformity, of course, a semicolon here. And if you know some really basic calculus, you'll know that the gradient itself will be, if x is greater than 0, it's 1, and if it's x is not greater than 0, it will be epsilon. So 1 or epsilon. Okay, we have this, and yeah, let me just return layer. Now we have the gradient itself. Okay, so I'll test this out. If there are any errors, I'll fix it. I guess we have them enough for this video, so let me just check this out. But before that, let me just write this relu grad here. So somewhere here, auto relu grad, and again it will take matrix of doubles, and here. Okay, all right. So I guess that's it for this video, and in the next video we will also create a softmax activation function, and after that we'll create forward and backward pass. I don't know how many videos it's gonna take, but yeah, we'll proceed further. Thank you for watching. Stay tuned for the next one.